approximately 4 times the receiving frequency. That means if you are trying to eavesdrop Wi-Fi systems, you must have something, you must have a local oscillator able to run at 10 gigs. That's not easy to do a stable oscillator at 10 gigs. Other problem is that the local noise. You have seen that in the schematic diagram, you have quite a lot of circuits coming from the TTL world, well, TTL or CMOS. Those components are very rich in phase noise. That means if you are trying to deal with very weak signals, it's very difficult to decode them. And that will be a problem if you intend to decode spread spectrum information. Because of the Shannon-Lindquist theory, the level of the signal is sometimes 10 dBs under the noise level. If you had some noise because of the switching of, for example, the Taylor demodulator and so on, Taylor mixer and so on, you cannot catch the signal anymore. That means we have to discover new components which are less noisy. Well, but this approach is a very low-end approach. It means something that doesn't cost a lot. A receiver like this one. Tomboy. That means four electronic parts. Cost less than $150. The only solution to have a lower noise and a better analysis is to ask to Mr. Seb Le Kernel some lesson about FPGA programming, because using FPGA offers you the ability to work directly on the signal just after the local oscillator. That's very important. You don't have a lot of noise in FPGA. The drawback is that you must know how to act with FPGA. Well, I hope it was clear enough. Sure, some questions.
Do you have any possibility to filter the input to the FPGA?
That's a general. Well, it depends on what the question was. Do you have any possibility to filter what you enter into the FPGA? The answer is yes and no. If you are working on a very narrow band signal, just build your filter yourself. That means you will dismiss the third harmonic at the input and completely kill any signal coming from the board itself, because the transients are not on the same frequency, or statistically not. But if you are working on military transmission or beginning to use spread spectrum systems, I didn't say military, well, any connection, submarine communications, well, very low frequencies, or on rigorous frequencies, you cannot, because you need to be wideband, and you have rejection. I just must precise that when I'm trying to deal with signals over 10 gigs, that means till 47 gigs, I haven't been able to go higher. I'm using Rubidium standards to stabilize the oscillator. That means quite a lot of money.
Can you buy online the?
Yes, everything is open hardware. The small system, which is a pure shortwave receiver, costs, I think, $39 shipping and handling.
And the other one?
The other one is a prototype, not yet, but it will. We're trying to, we are an association of ham radios. We're trying to give every software free, every development, our schematics are free. And we're even trying to make group buy to this with the price of the components. There are two parts in our research. One which is pure ham radio, and the other one which is dedicated to eavesdropping, hacking, studies on future networks, or networks who exist, like PLC.
I was wondering if you could just explain more. You said that you thought that if you got the signal directly into the FPGA, you would have a better signal quality.
And bigger bandwidth. That's the most important thing.
Pulling it in digitally, or you feeding a PLL inside the FPGA somehow? I guess I don't understand why that is.
I didn't catch the question, sorry. My English is very welcome.
So why do you think that bringing the signal into the FPGA will have a higher quality than if you were processing it in some other way?
It's a matter. Why should I use FPGA instead of this very low-end solution? Why FPGA?